My dear student friends, in continuation of my earlier lectures on the properties of transition elements or the D block elements, I would like to continue another important property which will be exhibited by these transition metal ions, and that property is called as color property. Color property. So the transition metal ions in their hydrated condition, that is when they are dissolved in water or when they contain the water, they exhibit variety of colors. For example, if I am going for the vanadium 4+, it will show the blue color, and if I am going for chromium 3+, it will show the green color. The hydrated ion is green in color. If I am going for Mn2+, it shows the pale pink color in hydrated condition. Similarly, cobalt 2+ show red, it is red in color, and iron 3+, it is yellow in color, and nickel 2+, it is green in color. Copper 2+, it is blue in color. Similarly, if I am considering the zinc 2+, it is colorless, it doesn't have any color. If I am going for titanium 4+, it is colorless. Whereas the titanium 3+, it is purple in color. Purple in color. So that means the majority of the transition metal ions, not only this 3D series, even including the 4D and 5D series, will exhibit the different variety of colors. For example, I will show you some of the salts which I carried. This is the Vanadyl Sulfate, which is blue in color. I think it is blue in color. I think you are viewing this color. It is a blue in color because it contains some water molecules. You will see the intense color when I dissolve this one in water, and for that I will take this solid material which is blue in color. It is called as Vanadyl Sulfate. I will take this one in a test tube. This is solid, and I will add the water. See, it is, you can see now it is a blue in color. So it is a Vanadyl Sulfate where the vanadium is present in +4 oxidation state. So similarly we can see, so this is the Vanadyl Sulfate. So the vanadium present in +4 oxidation state. Similarly, if I am going for, I don't have the chromium 3+ salt, so the Mn2+. So the Mn2+, it is the manganese chloride which I brought. It is pale pink in color. We can observe, if we observe this color very keenly, then we can see the very pale pink color. So if I am dissolving this one in water, this is the manganese chloride which I have taken in test tube, so it is hydrated. So you can observe, if a little water if you add, so it is slightly pale pink in color. So the concentrated solutions only you can see the pale pink color. So it is pink in color. And if I am going for another cobalt 2+, which you can see the very dark red color. So I will take this one in a test tube. and I will dissolve this solid, which is a crystalline solid. It also contains some water. So I will take, this is the cobalt chloride, and I will add the water. You will see a dark red color. See, this is the cobalt chloride. So it is the cobalt chloride, which is red in color. So the next salt I will take, that is nickel nitrate I brought, and you can see the beautiful greenish crystals in this. And I will take these crystals and into the test tube. So you can see the green crystals. And I will add the water. You will see the beautiful, the green color. So I will add water. So you can see a green color solution. So this is nickel, which is present in +2 oxidation state in the nickel nitrate or nickel chloride. And similarly, if I am going for the copper sulfate, this is the copper sulfate which I brought from your laboratory. It's the cupric sulfate, that means copper sulfate. So I will take this one in a test tube, which is a crystalline compound. So you can see the blue color crystals in this. So this is the blue color of the cupric sulfate. So this cupric sulfate, when I add to the water, the color will intensify. See, this is the blue color cupric sulfate. It is the blue color cupric sulfate. So similarly, if I am taking the zinc salt, so which is colorless, you are not observing any color, it is a white. And even if I am adding the water, so it is a colorless compound, it is the zinc sulfate, where the zinc is present in the +2 oxidation state. Even if I am adding the water, it will not show any color. The solution color is colorless. And similarly, if I am taking the ferric sulfate, so it is yellow in color. Ferric sulfate, it is yellow in color, and this is even in if I add the water, you can see the yellow color, that is the ferric sulfate, yellow color solution. So overall, among these different salts, starting from the vanadium 4+ up to the zinc, these will show the variety of colors which you observe. So I shown vanadium 4+, that is Vanadyl Sulfate, VOSO4, where vanadium is present in the +4 oxidation state. I shown the manganese, which is a pale pink color, even it's, I think you have not observed clearly. So that is manganese chloride, and cobalt chloride I shown, that is red in color, and Fe3+, that is FeCl3, I have Fe2, SO4 thrice, ferric sulfate, and I have shown the nickel nitrate salt, or even if you take the nickel chloride also, it is green in color, and copper sulfate, you have observed, it is a +2 oxidation state. Here also it is a +2, here iron is present in the +3, cobalt is present in the +2, manganese is present in the +2 oxidation state. And even you have seen the zinc sulfate, who is the solution color is colorless. So it is zinc 2+. So what are the reasons to show the different variety of colors when they dissolved in water or in their hydrated condition? And for that, I will do one of the experiment in order to make you understand the reason behind the color property. So for that, I am going to take the copper sulfate in a petri dish, that is a china dish, And here I will make an arrangement. This is nothing, it doesn't contain anything. So I will add, I am going to explain the reason behind the color property of the copper sulfate, and for that I will carry out the experiment. And here I am taking the copper sulfate, which is blue in color. Some of the crystals, little crystals I have taken. Now you are observing that with the help of spirit lamp, I have started to heat copper sulfate pentahydrate, which is present in this china dish. So initially you have observed that it is blue in color. After heating for few minutes, the blue color copper sulfate pentahydrate has lost its blue color and it is converted into almost colorless. Now I will transfer this material, that is the copper sulfate, into the test tube, and I will add the water. Let us see what happens. So that means after losing the water molecules, it has become color, that is the colorless. So now I will stop heating and I will transfer this copper sulfate into the test tube. So this is the copper sulfate which I have obtained after heating to remove the water molecules which are present earlier. So it is almost colorless. So water I am going to add to this one. Water is also colorless. And I am mixing the two colorless compounds. This is copper sulfate which is heated. This is the water which is also colorless. Now you can observe how, see, this is again, we are observing the regain of blue color. My question is, when two colorless compounds are mixing, then how we are going to get the color again? For example, if you mix the two different colorless paints, do you get a different color? No, the answer is no. So here, what is the reason for that? So that aspect is very important, and I am going to discuss the reason behind the color property of these transition metal ions when they get hydrated. So now you can observe the colorless, that is the blue colored copper sulfate which has regained its color. Stop. So the color property for the transition metal ions in hydrated condition, it is due to the formation of complex compounds. As I said, when initially copper sulfate has taken, which contains the 5 water molecules, it was blue in color. When you heated this one, it loses the 5 water molecules and it has converted into the water-free copper sulfate, which we are calling it as anhydrous copper sulfate, which is colorless. And again, when I add the water, it has again converted back into the blue colored copper sulfate pentahydrate. So that is what we have observed through the experiment. So that means these are the two colorless compounds. Water is also colorless. Anhydrous copper sulfate is also colorless. When we mix these two colorless compounds, we are getting the blue color back, that is the copper sulfate pentahydrate. So now we have to explain whether copper sulfate is responsible or water is responsible for the color property. You can, through the experiment, you can say water is responsible for the color property of the copper sulfate. Then how exactly? It is known that in copper sulfate, which is in the anhydrous condition, it is an ionic compound which contains the copper 2 plus ion separately and the sulfate ion also separately. It is an ionic compound. And in free copper 2 plus ion, it is a free copper 2 plus ion in anhydrous copper sulfate. So in the free copper 2 plus ion, the 5d orbitals are degenerate, that is in the free copper 2 plus ion, that is in the copper sulfate. These are degenerate. When copper 2 plus ion, it contains the 9 electrons in the d orbital, that is, it is having the 3d 9 configuration. So when 9 electrons are there, we can say this is 1 electron, second electron, third, fourth, fifth, sixth, seventh, eighth, and this is 9th electron. And so this is in the free copper 2 plus ion. So when you add the water, these 5 d orbitals which are degenerate, degenerate means equal in energy, ಎಲ್ಲದಕ್ಕೂ ಸಮನಾಗಿರುತ್ತೆ energy, ಎಲ್ಲ ಆರ್ಬಿಟಲ್ ಎನರ್ಜಿ ಒಂದೇ ಆಗಿರುತ್ತೆ. When you add the water to the anhydrous copper sulfate, these 5 d orbitals lose their degeneracy to form 2 sets of orbitals. So one is higher energy set of orbitals and another set of orbitals that is lower energy orbitals. And in lower energy orbitals there are 3 d orbitals, that is, and higher energy orbitals there are 2 higher energy orbitals. These 3 are equal, these 2 are equal after addition of water. But before addition of water, all the 5 are equal in energy. Now this is the energy axis. You can consider energy of these 3 orbitals are different and energy of these 2 orbitals, 2 sets of orbitals are different. Now this is also d orbital and this is also d orbital. Now out of 9 electrons, these 3 orbitals will accommodate the 6 electrons, and these 2 orbitals will have the remaining 3 electrons. So this is the energy difference between this higher energy d orbital and this is lower energy d orbital. And in terms of coordination chemistry, we are calling this one as T2G set of orbitals, and these 2 orbitals are called as EG set of orbitals in octahedral splitting. And this energy difference, this is called as delta O. So now, when water approaches the copper 2 plus ion, the splitting of the d orbitals has been taken place. Now, when the electromagnetic radiation in the visible region, that is 400 to 700 nanometer, this is called as visible region. When the electromagnetic radiation falls on that particular material, that is the copper sulfate solution, it absorbs, that is the electron present in the lower energy d orbital absorbs the electromagnetic radiation in the visible region, it will be 400 to 700 nanometer. Then this one of the electron get excited. It absorbs the energy, it will go to the higher energy. When it absorbs the energy, it is having the more energy and it will go to the higher energy orbital. And because of this excitation, because of the absorption of the radiation in the visible region means that is called as visible region. So only we can view the light, that is the color, when it falls in the visible region only. So when the energy difference between the higher energy d orbital and the lower energy d orbital corresponds to the energy of the light, then it will show the color property. So when it equals the energy of the radiation which is in the visible region, then only we can see the color property. And this energy gap is different for different metals. That's why the copper sulfate is blue in color, cobalt is red in color. So when the energy gap is different reasons, suppose copper sulfate is blue in color. If you look into the wagon wheel, that is the color wheel, you have studied in the lower class, that is a Vib Gayar. So I will ignore the indigo, it is a VBZYOR. So I am seeing the blue color, that means the color absorbed is that is the orange color. So if I am seeing red color means the absorption of the light in the green region. So the green region light, when it's absorbed by the particular electron, it gets excited to the higher energy d orbital, so it will show the red color. If a particular color is showing the yellow color, then it absorbs in the violet reason. So the color observed is complementary color, ಅದರ ಪೂರಕವಾಗಿರ್ತಕ್ಕಂಥ ಕಲರ್ ಬಣ್ಣ ಅದು ಕಾಣುತ್ತೆ. ಯಾವುದು ಅಬ್ಸಾರ್ವ್ ಆಗಿರ್ತೈತಿ ಅದು ಕಾಣಲ್ಲ. ನಮಗೆ ಯೆಲ್ಲೋ ಕಾಣ್ತೈತಿ ಅಂದರೆ ವೈಲೆಟ್ ಕಲರ್ ಅಂದರೆ ನಿಯರ್ ಟು 400. ಈಗ ನಮಗೆ ಆರೆಂಜ್ ಕಾಣ್ತೈತಿ ಅಂದರೆ ಅದು ಬ್ಲೂ ಅಬ್ಸಾರ್ವ್ ಆಗಿರುತ್ತೆ. ಬ್ಲೂ ಅಂತಂದರೆ ನಿಯರ್ ಟು 450 to 520 ನ್ಯಾನೋಮೀಟರ್. ಗ್ರೀನ್ ಕಾಣ್ತೈತಿ ಅಂದರೆ ರೆಡ್ ನಿಯರ್ ಟು 700 ಅಬ್ಸಾರ್ವ್ ಆಗಿರುತ್ತೆ. ಸೊ ಆ ರೀತಿಯಾಗಿ ಈ energy difference between the one higher energy d orbital and the lower energy d orbital, when it corresponds to the electromagnetic radiation, the visible region, they will show the different color property. So the color property arises due to the transition. This transition is called as DD transition. So the color property of the transition metals in the hydrated condition is due to the DD transition. Why it is called as the DD transition? Because electron is transiting or exciting from one d orbital to the another d orbital. These three sets of orbitals are also d orbital. These two sets of orbitals are also d orbital. So when the electromagnetic radiation falls in the visible region, it get the electron present in the lower energy d orbital, it get excited to the higher energy d orbital. And because of this transition, we are calling this one as DD transition. That is one lower energy d orbital to the higher energy d orbital. So the color property arises due to the DD transition when an electron in the lower energy orbital, lower energy d orbital, absorbs radiation in the visible region. Radiation in the visible region. When an electron in the lower energy d orbital absorbs the radiation in the visible region, it gets excited to the higher energy d orbital, higher energy d orbital, and this phenomenon of absorption of light occurs only when energy difference between two sets of d orbital matches the absorbed light, and such transitions are called as DD transitions. So the color property arises because of DD transitions. Thank you.